Okay, we are starting a unit on trigonometry here with sine, cosine, and tangent. So, like I just said, trigonometry, see if I can fit it on here and spell it right. Trigonometry is this type of math studying the relationships between side lengths and angles of triangles. And so, a little background information here. If you imagine a circle centered on the origin in the coordinate plane that has a radius of 1. So here would be the point -1, -1 down here, 1 here, and 1 up here. So the radius of this circle would be 1, which means if you draw a right triangle at any point on the circle using the x-axis and then the distance on the y-axis, the hypotenuse of that right triangle would be 1 as well. Okay, so then if we can look at the relationships between this angle right here, this corner angle. Here's a zoomed in version of this triangle. And we like to call that angle theta. It's a Greek letter. We'll use theta to describe that angle. It's just what's used typically in this type of math. Okay, so if we have this triangle with this hypotenuse of 1 unit, and then this angle theta, sine, which you may have heard before like a sine wave or a cosine wave, sine is just the ratio of the leg opposite the angle, so this leg here, to the hypotenuse. And if the hypotenuse is 1, then this just equals whatever sine theta is, this y value. So no matter where you draw this triangle around this called the unit circle, the distance between the x-axis and the circle vertically, the y value is sine of theta. Cosine theta is the ratio of the leg adjacent to the angle to the hypotenuse. That would be this down here, the x value. Okay, would be cosine, because cosine would be the distance here over the hypotenuse, which if the hypotenuse is 1, it just equals cosine theta. So wherever you draw this triangle, the distance right here of this bottom leg is called cosine theta. And then tangent is the ratio of the leg opposite the angle to the leg adjacent to the angle. So it really is like sine theta over cosine theta. It's just those two numbers as a fraction. So tangent would be sine theta over cosine theta. That would be the tangent. Okay, now this is really just some background information about where these functions come from and why we care about them. Because they give us these values, this ratio, no matter where we draw that triangle, that's what that ratio is. And so it creates all these types of relationships, and you can plot this out as a graph, and that's where the sine wave and cosine waves come from. And so that's something interesting. If you want to look into that further, you can search for diagrams and things like that. But for our notes today, we're just going to be using these functions to determine missing values of right triangles. So this is where these functions come from, this simplest version of a right triangle where the hypotenuse is always equal to 1. And this is why these functions work. But for our purposes for today, it's not really necessary to know this background information, but I find it a little helpful just to know that it's coming from somewhere, right? We're not just making these numbers up. And so we can use a mnemonic device to help remember which values to use for each of these functions. And like I said, theta is a Greek letter usually used to name this angle, this inside angle. So when we talk about right triangles, we usually say sine or cosine or tangent of theta. So again, sine is the ratio of the leg opposite of theta, the angle, to the hypotenuse. And so sine would be opposite over hypotenuse. And so you can remember that as SOH, sine opposite and hypotenuse. Okay, so that's how we get that ratio. And if we're talking about opposite and hypotenuse in terms of the angle theta, which if you think of it as, like, say, this corner here, sine of theta is the opposite side over the hypotenuse. Now, cosine is the ratio of the leg adjacent to the angle over the hypotenuse. So we have adjacent, which just means next to. Okay, so it's adjacent over hypotenuse, and you can remember ca, C-A-H. So that would be cosine adjacent and hypotenuse. Okay, so far we have so, ka, and then we have toa. SOHCAHTOA is our whole mnemonic. The tangent would be the ratio of the leg opposite over the leg adjacent. So no hypotenuse involved. Opposite over adjacent. So the tangent is the opposite over the adjacent. Okay, excuse the messy small handwriting here. Didn't leave myself much room. But we have SOHCAHTOA, so the sine function is the opposite over the hypotenuse. Cosine is adjacent over hypotenuse. Tangent is the opposite side over the adjacent side. Okay, so SOHCAHTOA, if you can remember that, then you can think about each part of that mnemonic and part out what ratios you use for each function. Okay, so here's how we actually use this to find or to deal with right triangles. So first we'll just practice writing these ratios out. We're going to write our answers both as a fraction and as a decimal. So it'll be helpful if we get a calculator out here. Okay, so this says sine of A, so sine of angle A. So here's angle A. So we're going to look at this triangle from the angle A's perspective here for our sine. And remember, sine is opposite over hypotenuse. So the opposite side from angle A is 4, and the hypotenuse of this triangle is 5. So the sine of angle A is 4 over 5. And if we want to write that as a decimal, 4 divided by 5, 0.8. Okay, now we'll do sine of angle C. Here's angle C. Again, sine is opposite over hypotenuse. So the side opposite angle C is 3, and the hypotenuse is 5. So 3 over 5 is 0.6. Okay, now we'll go to cosine of angle A. Cosine is the adjacent side over the hypotenuse. So if we're looking at angle A again, the adjacent side here is 3, and the hypotenuse here is 5. So 3 over 5. Notice how we switch to the other angle. This is the same as sine of angle C. Cosine of angle A is the same as sine of angle C. So depending on which angle you're talking about, you'll often get the same value for a different one. Okay, and then we'll do cosine of angle C, which is again adjacent over hypotenuse. So it's going to be 4 over 5, which again is 0.8. Now we'll go to tangent. Tangent is the opposite side over the adjacent side. So the tangent of angle A, we're going to have opposite is 4, adjacent is 3, so 4 over 3, which would be 1.9, oops, not that, 4 over 3. 1 point, that looks better. 1.3 repeating because it is a third as a fraction. That's going to give you a repeating decimal. So we can just say 1.3. If you want to put that repeater bar above it, that's fine too. But 1.3 would be okay. And then tangent of C, opposite over adjacent, is 3 over 4, which would be 0.75. Okay, so remembering how those ratios work, it all depends on which angle you are using as your perspective. And then you're looking at the opposite or the adjacent side to that angle, as well as the hypotenuse. Now let's actually use this to find the value of some angles that, we don't know the side lengths, but we do know the angle. And really, you normally just use your calculator for this. So the first one says tangent of 43. So it would be 43 degrees, a 43-degree angle. We're trying to find the tangent of that angle. And if you think back to our unit circle with our x and y axis here, a 43-degree angle means that whatever angle this is right here, that's 43 degrees. We're finding the tangent, the ratio of this side over this side of whatever this triangle is for a 43-degree angle. So that's where these numbers are coming from. That's why they're important. It's not just a random function on our calculator. They are coming from a real triangle you could draw in the unit circle. So to find this with this type of calculator, we're going to put 43 in, and then you have a little trigonometry drop down here, and we choose the tangent, and we get 0.93251 and so on. So we'll just round that. Let's say it says round to the nearest tenth. So that's fine. We can do 0.9. For our purposes, that is good enough. Cosine of 17. So again, a 17-degree angle. We're finding the cosine. That would be the ratio of the adjacent angle, or the x value, over the hypotenuse. So the cosine of 17 degrees, 0.956, and so on. So let's say, now that rounds up to 1.0. Leave it like that. Tangent of 82, 7.11, so say 7.1. Sine of 37, here we're using a sine for the first time. Again, just pick the sine function. 0.60, so 0.6. Sine of 74, 0.96, so again, that goes to 1.0. Cosine of 66, 0.40, so 0.4. Sine of 90. Now this is a 90-degree angle. You'll see what happens here. The sine of that is 1. And that's because, again, if you imagine our little unit circle, remember the sine of a 90 degree. So the angle here is 90, which means we have, it's kind of moved all the way up to the axis. And so we kind of have a straight little line of length 1. And so the ratio of whatever to the hypotenuse would be 1 over 1. So it's kind of reached the y-axis there. Our cosine of 90 gives us 0. And that's because that x value for the same type of situation would be right at 0. And the tangent of 90 says invalid input. And that's because if you remember what we said up here about tangent, it's sine over cosine. And so we're doing 90 degrees here. And if you have 1 over 0, that doesn't work. So there is no tangent at 90. You can put the empty set symbol or no solution or NA, or it doesn't work because you can't divide by 0. So that tangent function at 90 degrees doesn't exist. And if you ever look at the graph of a tangent function, it looks something like this, where you have these separate discrete pieces because there's certain points at set intervals where the function doesn't exist. All right, so that's how you use a calculator to evaluate trigonometry functions. Let's actually use this in a more concrete way and find missing side lengths of triangles. And so it'll be good to remember our mnemonic, SOHCAHTOA, for what we need to find. Okay, so here's how we do this. We've got this 52-degree angle here. And so we're going to use one of our functions of 52, and we have to look at what sides we know. Okay, so what we have is the hypotenuse here, that's 16, and then we have the adjacent side here is x. So we want to use adjacent over hypotenuse, and that would be our CAH ka part of this mnemonic. So katoa, which is our cosine function. So we're going to use cosine of 52, which is, again, adjacent over hypotenuse, so x over 16. All right, so what we're going to do is evaluate the cosine of 52 on a calculator. So 0.61, blah, 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 blah. And in order to solve for x, we multiply both sides of this equation by 16. So I'm going to multiply cosine of 52 times 16, and I get 9.85, or 9.9. That's what we do. So you're going to make a ratio and then solve for x. Okay, for example B, we have a 55-degree angle. We're not using our hypotenuse. We have our adjacent side here and our opposite side here. So we're going to need to use the tangent function because we have opposite and adjacent. So we know that the tangent of 55 is going to be equal to opposite over adjacent, so x over 20. And then again, to solve this, we're going to multiply both sides by 20. So on my calculator, I have to find the tangent of 55, which is 1 point, nope, did a little too much. Make sure you clear your calculator first. Don't do what I just did. So the tangent of 55 is 1.42, etc., times 20. And that gives us 28.56, so 28.6. All right, example C. Just make sure your answer seems reasonable. I mean, there's really no way to know for sure. But since this side's 20, 28.6 seems appropriate. Here we had 16 and then 9.9. That's good. The hypotenuse is always bigger, so it seems reasonable. You know, you're not going to know for sure because we're just doing stuff in the calculator and we don't have the other side. But, you know, if you get a number that's in the hundreds and your original number is here 20, so that would give you a red flag. Okay, so here we have a side length of x. We have a 55-degree angle over here. This is the hypotenuse, is 13, and we have our opposite here. So I'm going to use the sine function. Sine of 55 is equal to our opposite, which is x, over the hypotenuse, which is 13. So I need to multiply both sides by 13. So sine of 55, which is 0.819 on and on, times 13 gives us 10.6. Okay, we'll do 3 more. 37-degree angle, and it's my adjacent side and the hypotenuse. That'd be a cosine. So CAH, cosine of 37 equals the adjacent side over the hypotenuse, so x over 10. Notice all of these are right triangles. This has to be done with a right triangle. So if you have a non-90-degree non-right triangle, this won't work. So the cosine of 37 times 10. We get 7.98, which rounds up to 8.0. And this is one reason why often you'll have directions to round to the nearest hundredth. So instead of 7.9 rounding up to 8.0, I would have rounded to 7.99. But either way, it's okay. For our purposes, nearest tenth is fine. All right, for example, E, we have a 33-degree angle. We have adjacent and opposite. So we'll be using our tangent. It's the one that doesn't use the hypotenuse. So the tangent of 33 is going to equal 12 over x. right? TOA, opposite over adjacent. So if you notice here, I have x on the bottom. I'm going to have to do a little bit more algebra, unless you just know how to rearrange it. So if I multiply both sides by x and then divide by tangent of 33 on both sides, essentially we're just switching the tangent and the x. So we have to just divide by 12 divided by the tangent of 33. So I have x equals 12 over tangent of 33. Okay, so I'm going to say 12 divided by 33, and then I'm going to hit tangent, and then equals 18.5. So x equals 18.5 here. A little trickier, but when x is on the bottom like this, you really can just switch the x and the tangent or whatever the function is, and then you'll just be able to divide it out. And last one, we've got our 70-degree angle. We have the opposite is 18, and the hypotenuse is x. So this is a sine function. So sine of 70, and sine is opposite over hypotenuse. So 18 over x. Similar situation. Because of this algebra we did over here, I'm just going to go ahead and say x equals 18 over sine of 70, right? I can switch that. And if you think about sine of 70 over 1, if you were going to solve this proportion using the cross multiplication trick, you would do 1 times 18 and then divide by sine of 70 anyway, which is essentially what we're doing right here. So 18 divided by the sine of 70 is 19.2, which is the hypotenuse here, and it is bigger than 18, so it works out. So that's a quick rundown of how to use sine, cosine, and tangent to find missing side lengths on right triangles. So as long as you remember the mnemonic device, SOHCAHTOA, sine opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent opposite over adjacent, you'll be okay.